Okay, hello everyone. Let's go ahead and take a look at displacement and distance from velocity. Now let's go ahead and just start off with something that is not necessarily calculus related. Let's say, for example, that we have what we know to be true as the distance formula, which is usually referred to as d is equal to the rate times by time. Now, if, say for example, the rate was 2 and t was 3, what is the distance traveled? Okay, now I'm going to go ahead and just draw this so that we get a visual representation of what's happening. And notice that here I'm putting a rate, which is kilometers per hour. And notice that the rate is always going to be 2. So notice that it's constant. It's 2 all the time. And then we know that this particular particle is traveling for 3 hours. Let's just say that's in hours. And so what happens then is that I'm actually coming out with this right here, this shape, because it starts off at 0 and then it travels for 3 hours. So of course, if we were to go ahead and use that formula d is equal to r times t, we would come up with 6. Now, if we go ahead and think about where that 6 is represented visually, well, it's just the area that is created by the rectangle here, because we know that the rate is a constant rate. We know that the time is from 0 to 3 hours. That creates a rectangle. The area of that rectangle now becomes the distance traveled. So let's go ahead and think about what that means then. It says that in order to calculate distance or displacement, we need to calculate the area under the velocity curve from one particular time to another particular time. So again, notice that what we're dealing with now is we're dealing with area under a curve that is being bounded by two different values. So what is that? Well, that's the integral. That's the definite integral. So what we're going to say then is that displacement then is going to be the integral, the definite integral from a to b of the velocity function d of t. Okay, we're also going to say that the distance is going to be equal to the integral from a to b of the absolute value of v of t d of t. Okay? Now, also, let me go ahead and just throw something in there just so that we can also see where this is coming from in terms of the integral beyond the geometric interpretation. Remember that we said that as the velocity is going to be the first derivative of the distance or displacement function, then what we can say then is that if we actually integrate both of these, then the displacement of the distance function is just going to be the integral of the velocity function d of t. And that's going to be consistent with what we have there. Okay, so let's go ahead and take a look at an example here. Let's say, for example, our velocity function is going to be v of t is equal to negative t plus 1 on the closed interval from t is equal to 0 to t is equal to 2. Now, there's going to be two different things that we want to go ahead and take a look at, one at a time. We'll first take a look at displacement, because displacement is going to be much simpler to integrate. Now, if we go ahead and actually use the same idea here in terms of displacement being actually the integral from a to b, and in this case a is 0 and b is 2. And then we're going to integrate the velocity function with respect to t. So I went ahead and drew the velocity function here. Now remember that what we said is that area under the curve that is bounded by a and b can be positive or negative depending upon where it is with relationship to the x-axis. So what I've done here is I've shown all the positive area, or the positive distance in blue, and the negative area, or the negative distance in red. So if I just go about doing this, integrating, finding the antiderivative here, which is negative 1/2 t squared plus t, and if I use my fundamental theorem of calculus to go ahead in order to determine what the area will be from 0 to 2, I substitute the value of 2 in first into the antiderivative, which is negative 1/2 2 squared plus 2, minus, of course, if I substitute 0 in here, that's all zeros. So what I come up with is negative 2 plus 2, which is 0. Now, that makes sense because of the fact that what we have here is this shape right here and that shape right there. They're identical. One is a positive area, one is a negative area, therefore the areas will cancel each other out to come up with a displacement of 0. Okay. Now, let's juxtapose that with what we have with distance. Now, if I go ahead and take a look at exactly the same thing here, what I need to do is I need to make sure that whatever negative area I have, I need to make that negative area positive. Now, in order to do that, what can I do? Well, there's a couple of ways, but probably the easiest way is just to go ahead and multiply the negative area by -1, so therefore it becomes a positive value. So that's exactly what I did here. Look at what happens. Notice that the positive area, which is from 0 to 1, of the velocity function d of t is right there. Okay? The negative area, notice I'm separating the two, the negative area now is the same integral except for it's going from 1 to 2 of the same velocity function d of t, but notice that what I'm doing is I'm subtracting because I want to make sure that this area here, which is originally a negative area, becomes a positive area. So if I do the antiderivative for both of these and I evaluate the definite integral using the fundamental theorem of calculus, notice that what I come out with is I come out with the value of 1. So notice that with displacement and with distance, you're coming out with two different values. One is going to be a 0 value, one is going to be a 1 value. So it's going to be important for you to know what the difference is conceptually. So that's one of the things that I want you to go ahead and think about, and we'll discuss in class. How would you describe the difference between distance and displacement now that we know we can actually calculate those two using definite integrals and the fundamental theorem of calculus? Okay? So I'll leave that for you to think about and for us to discuss in a subsequent lesson. Okay? So give it your best shot. We'll see how you can do with displacement and distance from the velocity function. Okay? Give it your best shot. See you next time. Bye-bye.